Infinity in the cosmos. I am intrigued by the infinity symbol and what it means. Its ancient Greek origin is known as the Ouroboros, which looks like a tau devouring a serpent. Its Latin origin, infinity, is infinitas, which means unboundless, endless, limitless. Archimedes was aware of the concept 2,300 years ago, and Galileo is known to have considered it. But it wasn't until 1655 that John Wallis coined the phrase the Lenin skate, which is what we know today as the infinity symbol. We don't actually know the origin of the infinity symbol really. It's possible that it has Greek origins, such as the letter omega, which is the last letter in the Greek alphabet. It has the appearance of a snake, twisted horizontally into a figure of 8, so it looks like a serpent. And it's a fitting depiction of the idea of endlessness, of boundlessness, eternity. It's not too dissimilar from the concept from Tibetan Buddhism of the endless knot, the interweaving of the spiritual path, the flowing and movement of time with that which is eternal, the endless cycle of suffering, birth, and death and rebirth, as they believe in reincarnation. The mathematical properties of the infinity are very interesting. There are actually various types of infinity based on the type of number system you're looking at. Real numbers, whole numbers, rational, irrational numbers. But if we just consider, for example, mathematical infinity and compare that to what is known as in coordinate geometry as translational systems, that is a coordinate transformation, one starts to ask the question, does infinity really exist? For example, in stars, which become black holes if they are of a certain mass above about 3 times the mass of our sun, it is possible to generate an infinity, an infinitesimal density at its core. What does that really mean, and do we understand it? The mathematical equations show this. But is that really what happens? It's possible to do something called a coordinate transformation and actually make the infinity go away. In fact, the original black hole equations, known as the Schwarzschild solution, is actually transformed into something called the Einstein-Rosen solution if you do what's called a coordinate transformation on that equation, and you can remove the infinity. We'll come back to black holes in a moment. But let's just consider the interesting concepts of a zero and an infinity. We think of zero as meaning nothing. There is nothing there, it's empty, nothing to be counted. Zero goes back a very long time, but the ancient Babylonians didn't originally have zero in their number system. They invented it a little bit later. But zero is kind of the opposite of infinity. Infinity is the biggest, for example, thing you can have, the largest number. If you try to count all of the blades of grass in a field, you wouldn't be able to. There's too many. That's kind of infinity. That's the idea. Or the grains of sand on a beach. But you can study the interesting properties and relationships between zero and infinity. For example, a zero multiplied by infinity is zero. Zero plus infinity is infinity. Infinity minus zero is still infinity. What's really interesting is when you look at the properties of dividing by these interesting numbers. So you can look at a summation of a series. For example, if you look at the sum of 1 over x as x tends towards 0, the solution tends to infinity. Similarly, if you look at the sum of a solution of 1 over x as x tends to infinity, the solution tends to 0. Just think of that in your head for a moment as 1 over 0 tending towards infinity and 1 over infinity tending towards 0. In other words, if you divide by something that's very, very large, you end up with something that's very, very small. And if you divide by something that's very, very small, you end up with something that's very, very large. And you can start to consider some variations on these themes, such as 1 over 0 tends to 0. 1 over 1, well, that's just unity, 1. 1 over infinity tends to 0. Infinity over 1 tends to infinity. Infinity over 0 is 0. Infinity over infinity is infinity. And of course, 0 over 0, well, that's just nothing. That's 0. Mathematicians and physicists use these kind of ideas to think about what happens in stars. And I mentioned black holes earlier. And so when you look at a gravitating mass like a star, and when it gets to the point of collapse, you can consider what happens to the trajectories of particles around it. All of our satellite mechanics and dynamics is based on these ideas, whether it's the moon going around the Earth, or the Earth going around the sun, or a space station in orbit. We use these equations, and they describe the equations of motions of particles or objects around a gravitating mass. The particular equation which we use for black holes is known as the Schwarzschild solution, and it's very interesting. It essentially is an equation which describes the geometry around that gravitating mass. And without going through all the details, let's just consider that it has a temporal component and a spatial component. What's really happened is very interesting because in the temporal component, for example, you get a term in a bracket which is 1 minus r over rg. Now the r is simply the radius from the center of the object of the star, which is extending out towards infinity in space. And as you move towards that object, you are moving along a line of r, of radius r. At some point, you hit a radius from the center of the star called the gravitational radius, so that's the rg. And at that point, r is equal to rg. And so what you end up with is 1 minus r over rg, which basically tends towards 0. And so the temporal component of the equation comes to 0. What this means in reality is that from the perspective of a distant observer who's watching, say, a spacecraft approaching a black hole, time stops at the event horizon. It doesn't actually stop for the spacecraft, but from the perspective of the distant observer, which is how these equations are written, it does. Let's look at the spatial component. Well, that's also a 1 minus r over rg, but the difference is the whole term is inverted, so it's to the power of minus 1, or 1 over 1 minus r over rg. So now as r equals rg, you end up with 1 over 0 tends to infinity. And that's where you get the singularity at the center of the black hole. That's what we believe is that what happens to black holes. You have an event horizon where time seems to stop from the perspective of a distant observer. And you end up with an infinite density and compression converging spherically symmetrically towards the center. Now these are really interesting concepts, and it's how scientists think about black holes. And there's people who now look at whether those infinities really do exist. And of course you can apply them to the entire universe. We believe our universe expanded from the Big Bang, when the universe was very small in scale. And essentially you can take these similar equations for the entire universe, and you can show that the universe had to start off very small. For all intents and purposes, it was a singularity. Well, I find it interesting that the universe started off as a Big Bang, and then it expanded. Space and time and energy and matter were created along the way. And then we have everything we can see today, the stars, the galaxies, and life like us. And we can make predictions about the future based on what we can measure and what the end state of the universe is likely to be. Well, it seems to me that it's entirely possible that everything that we regard as material is actually not important. It's only important from the perspective of us, as we exist in this relationship, and our existence requires functional relationships and forces between things. Hence you have the laws of physics acting. But actually, we know that matter and energy are equivalent. Einstein taught us that. And we also know that space and time are equivalent. Einstein also taught us that. So actually, what is there? Can it be argued that all there is space? Let's just consider that for a moment. Imagine there is nothing. There is a void, an emptiness. And it's a volume of space with nothing else in it. So it has no direction of time, it has no matter, no energy. Now imagine you place something in it. And then you place something else in it. So you've now placed two particles, say, or two objects, or two things into that volume. You've now had causality and effects. One event followed the other. That essentially sets the direction of time flowing. So by this kind of thinking, it seems that time would come after space. The time would not exist without space, without things happening in space. Now if we consider that in the context of the universe underwent its Big Bang inflation at the beginning, and it was full of energy. At some point, the universe cooled sufficiently so that matter could decouple from the radiation, and you had the first particles like hydrogen and lithium and helium. And these were the first material things in the universe that had the potential to go on and become other things, such as molecules and dust, and eventually everything we can see. Well, let's now consider the future of the universe. What does science and astronomy tell us about that? Well, it's really interesting because we know that eventually all black holes will thermodynamically decay. And we know that all objects, all galaxies, all planetary masses, everything we can think of will eventually decay. And actually, as the universe continues to expand and it gets colder and colder, all there is left is no matter, only photons. Everything eventually decays into pure photons. So you've got a situation where you have, at the beginning, space, and then time, which are unified into space-time. Then you have the energy through the hot Big Bang. Then it cools as it expands, and you have matter. And then you have things and objects like us, and planets and stars, and everything else we can see. And eventually, the universe gets bigger and bigger, continues to expand, and it gets cooler and cooler. And the matter goes back into energy. And perhaps then time and just space. So maybe space is all that's left, just like it was at the beginning. Now if we look at the infinity symbol, which we discussed earlier, it's an intriguing construct because it looks like this serpent that's devouring itself, tail and a head. But it's also interesting because it looks like two zeros next to each other. Well, what if all there was space at the beginning? and there was nothing inside of it? And what if the universe also expands into nothing but space, and everything decays into pure energy, and then even the last photon, it doesn't exist anymore? And so we've got space again. So we have a curious phenomenon where there is nothing which turns into everything, which then decays back into nothing. Now, if you were an entity, a god, a meta being, some creature which had the power, the knowledge to create universes in the way that, say, Oliver Stapleton talked about in his novel Star Maker, the best way to do it would be if it didn't cost you energy at all. If the actual process of creating a universe, it essentially creates all of its own energy intrinsically to it, and everything that it needs from that process. And then when it's done with that universe, it decays back into its background, and there's nothing else left. And so if you then wanted to create millions of universes, a multiverse, it becomes economical because it doesn't cost anything. All of the energy that is given to create in any individual universe is eventually given back. So maybe when we are searching for our grand unified theories and our very complex ideas that we're trying to put together from theoretical physics, and we are guided by principles such as beauty, this is what a lot of physicists like Paul Dirac, Richard Feynman believed in. But maybe we should be looking for simplicity. Maybe that's how you produce complexity, from simplicity. So perhaps the idea of creating a universe comes from something very simple, a very simple idea. Let's just consider, for example, what Richard Feynman called the greatest equation, or the most amazing equation in physics, which is the Euler's identity. This is e to the I pi plus 1 equals 0. The e is the natural base of the natural logarithm. I is the imaginary number. I squared is equal to minus 1. Pi is the irrational number. 3.14157, etc. 1, of course, is unity. And 0 is 0, nothing. We have an equality symbol. We have an addition symbol. If you take the 1 over to the other side, it becomes a subtracted symbol. There is multiplication and division in this equation. This equation is quite remarkable because it does contain many of the elements of mathematics that we need. But essentially you have e to the I pi, says e to the power of an imaginary number multiplied by some irrational number, plus 1, which is the smallest number we can think of as a whole number, gives you 0. I mean, maybe something like that is how the universe is created, from an equation so simple. And so we can consider these ideas. And I think that the universe is a beautiful place, and we see much complexity to it. But I also think that its origin and its future evolution is probably so simple, and is probably known to us for many centuries. But we couldn't accept it because we're always looking for the complicated. And maybe it's as simple as thinking about the juxtaposition of relationships between 0, 1 and infinity. Well, I know that my lifetime is short. Certainly is an infinity. Indeed, the age of the sun upon which I am orbiting is only billions of years. That's not infinity either. The universe is 13.8 billion years old. Who knows how old it will live to? Double that, perhaps. Is that infinity? I guess infinity is relative to whatever you want to measure it reference to. So I won't exist in an infinite lifetime, but perhaps from the perspective of a fly, you may only live for 17 days. I have an infinite lifetime. This really gets to the heart of time, of course, which is a very complicated idea. So I will end this podcast by just saying that I think infinity and zero and how they relate to each other is very interesting. And a lot of our mathematics and our inability to progress our physics ideas is actually due to zero and infinity and our failure to understand it. Our failure to solve equations, whether it's in quantum electrodynamics or in plasma physics, all kinds of fields, is usually down to infinities. So we have to invent mathematical tricks such as renormalization in order to, say, predict the correct particle masses of electrons. So I think we ought to go back to philosophy and think more about the foundations of these ideas and what they mean. And perhaps when we go back to simplicity, we can have a chance of understanding the very complex, which is everything we observe and everything we exist in and have ever known and ever will know, but which may itself be, as the Tibetan Buddhist said, like an interweaving path of flowing time movement, of endless eternal cycles in a huge multiverse of universes, which go on and on and on, and for which, although there is an infinity of them, and they each expand to their own infinity, they actually all contain zero. And that's all there is to everything. It's zero. Well, just like the serpent eating its tail, we can certainly devour ourselves thinking about these ideas and sending ourselves around in circles. Well, there it is again, the circle. It seems we always come back to that geometry, whatever we look at. There's probably only one thing we can say for sure, and that is whoever created the universe, or whatever created the universe, or whatever its nature is or was, it had to have been a mathematician.